The experiment that we will be conducting today is the preparation of competent cells. Okay, so this is usually done with a pure culture, and what we have got in our lab is TH5 alpha or top 10 cells. So these cultures have been maintained as glycerol stocks, and they have very specific genotypes. And we try not to revert the genotypes by keeping those cultures pure under very specific nutritional conditions, and the cultures are revived every 6 months to revive the cultures that we use for making competent cells. Okay, so there will be two methods that will be used for the preparation of competent cells. Method number one will be the preparation of competent cells by calcium chloride method. And the second method that we will use is electrocompetent cells. Calcium chloride method is quite an old method, but the limitation is that we cannot transform big DNA molecules through calcium chloride. It just increases the pores a little bit, and the small plasmids having some inserts smaller than 6 kb can be transformed through this method, calcium chloride method. Electrocompetent cells, on the other hand, it is used by the laboratories which have appropriate equipment for this technique, okay, because it requires a high power voltage booster to give an electric shock to the cell, okay, under confined conditions, and it's a costly equipment. So every lab does not have, but because the FC has got it, so we are not using calcium chloride method as a standard method for routine transformations, but we are preferring the electrocompetent cells for transformation purposes because they give excellent transformation results. Okay, so anyway, I will be talking both about the calcium chloride method as well as electrocompetent cell preparation method. So the first, I will emphasize that how we will do that practical. In this case, the cells of BH5 alpha or top 10, these are both E.coli cells, okay? These cells are inoculated a day before you go for the preparation of competent cells, and the optical density of these cells is brought down to 0.45 to 0.5 by making a fresh secondary culture. What it means is that from the primary culture, that you grow overnight, we make a secondary culture, okay? That is we can take 5 to 10% of the inoculum from the primary culture to get a secondary culture, okay? And if we use this much inoculum in about 2 or 3 hours, we can get an optical density of this one that I have mentioned here. And then we can readily make the chemically competent cells from the cells which have been grown to this optical density. Okay, so this was some of the introduction about that how we proceed with this chemically competent cells. For the preparation of the bacterial culture is very important, and that's what I have mentioned here. After you have reached the optical density of 0.45 to 0.5, what you do is that from the flask, you take the 30 ml cells into a falcon tube, which is having a total capacity of 50 ml capacity. But we take 30 ml of the liquid culture into this tube. We spin this tube from 3000 to 4000 RPM. And we collect the pellet, which is at the bottom of this falcon tube, and it is visible like a big pellet because it is from 30 ml of the cells. So it's very clearly visible, but it is very compact, yellowish pellet. Our next step is that we suspend this pellet in 30 ml of 0.1 molar calcium chloride, which is chilled on ice. So that is called ice cold calcium chloride, and the molarity is 0.5 molar, and we gently suspend these cells in this chilled calcium chloride solution. And we go back again for centrifugation at 4000 to 5000 RPM. So there is no incubation required actually. During the resuspension process, the cell gets treated with calcium chloride, and one of the good indication that the cells have been treated well with calcium chloride is that the cells now become whitish in color. They are fluffy and they don't settle down after spinning. Okay, very well. So when you spin those cells after treatment with 30 ml calcium chloride and you look at the falcon tube, 50 ml falcon tube, you will see a big pellet. It's very fluffy, very fragile, okay? And it is the cells, they are completely whitish. If you see that conformation of cells, it means that your calcium chloride treatment is perfect, okay? If you see a pellet at the bottom, just like a pellet you saw here, it means your calcium chloride has not worked. So this is one of the indications that your cells have worked. Now, what you need to do is that this is one treatment, you spin the cells and then you decant. You decant the supernatant, okay, and collect the pellet. Now you can resuspend the pellet in 10 ml of ice cold calcium chloride again, which is 0.1 molar, okay? So it means that you get the pellet from the original culture, You treat with 30 ml of calcium chloride, which is 0.1 molar, spin it and collect the pellet, treat that pellet again with 10 ml of calcium chloride. Resuspend the cells, and after resuspending all that, you spin it again at 4,000 to 5,000 RPM. So you have cell suspension in 10 ml in the falcon tube. And in this falcon tube, now the volume is up till 10 ml. You spin it at 4,000 to 5,000 RPM. Collect the pellet and this one. So you collect the pellet and then resuspend the pellet in 2 ml 0.1 molar calcium chloride. And remember that this calcium chloride is always chilled to ice, in ice. Always use cold, ice cold calcium chloride to protect your cells from bursting out, okay, and stopping the metabolic processes within the cell, because we don't want the cell wall to become thick. At an optical density of 0.4 to 0.5, the cell wall is thin, okay, and calcium chloride treatment opens the pores in the cell wall. So the opening of the pores is dependent on the treatment, age of the cells, okay, and your best competent cells will then take a total size of about 9 kb of the plasmid size can be taken up by this one. It means 3 kb is the size of your plasmid, and you can have 6 kb insert if you have prepared real good cells. Now what you need to do is that after resuspension the cells in 2 ml of calcium chloride, you need to aliquot these cells in append of tubes. And you take 200 microliter of these cells from here and dispense them to each of the different tubes. So you can make actually 10 tubes by piping out 200 microliter out of this 2 ml. And now you can put these tubes at minus 80 degrees centigrade until you are ready to use these competent cells for your transformation experiments. Okay, so this is one of the methods which is called chemically competent cells method. Okay, the second one is the electrocompetent cell preparation that I'm going to elaborate now. The transformation in electrocompetent cells is based on the fact that you have a thick cell wall of bacterial cells, okay, and then those cells should be suspended in water which is devoid of any ions in it, because we don't want the electricity to flow through the cells, okay, and this may cause bursting of the cells. So if there are any salts remain in the cell suspension, it will cause greater flow of electricity, and greater flow of electricity will result into greater heat as well. And that heat is responsible for bursting the cells. So we need to clean our cells again and again with distilled water. Okay. So what we do is that out of the flask, we can take again in the Falcon tube about 30 ml cells, the same way we took for the electrocompetent cells. Okay. And spinning of the cell is always from 3000 to 4000 RPM for 5 minutes. Whether it is the preparation of electrocompetent cells or calcium chloride method of preparing the competent cells. The cells don't get any compression effect, and they don't get burst due to the compression of the G force which is applied on the cells. So this revolution per minute is very much important whenever spin the cell for preparation of the competent cell. Okay. So these 30 ml cells, you spin it and you get the pellet, decant the supernatant, you just decant it and resuspend the cells again in 30 ml of ice cold water. Resuspend those cells gently, not vigorously. The optical density of the culture in this case is from 0.8 to 0.9. It means that the cells are at actually late log phase. You are harvesting the cells at this point. In case of chemically competent cells, you harvested the cells at this point. At the early phase of growth, the cell wall is thin. At the late growth stage, the cell wall is thick and the growth is almost going to be stationary. Okay. So this thick cell wall is required for electrocompetent cells. A thin cell wall is required for chemically competent cells. Okay. So we started here with an optical density of the cells from 0.8 to 0.9, spun it once, suspended the cells in 30 ml of chilled water. That chilled water is double distilled deionized water, so that it should not have any ions to restrict the flow of electric current through the cells where we are doing transformation or electroporation, in other words. Now, again, what you do is spin this tube at 4000 to 5000 RPM. Collect the pellet, and this is a compact pellet. It's not a fluffy pellet as is in the case of calcium chloride treatment. Okay, this is a hard pellet. So what you can do is that you can wash it again with 30 ml of ice cold water. Give another spin at 4000 to 5000 RPM. And you get the pellet. And the third time, what you do is resuspend the pellet in 2 ml of ice cold double distilled deionized water, and you can dispense this 2 ml into 10 tubes using 200 microliter per tube. And you need to store these cells again at minus 80 degrees centigrade, and you can pull one tube whenever you want a transformation and do the electroporation in it. Okay, so we will not be doing transformation in this experiment, but we will use these tubes later on in another experiment where we will be doing transformation both using the electrocompetent cells and the chemically competent cells. So we will include it in another experiment. So let's go to the lab and start this experiment now. Okay, we are ready for the experiment, and what she has managed in this laminar flow is that we have the bacterial cultures, and this one is the one which was grown overnight, and it has an optical density of greater than 0.8, and this was used as a primary culture to grow a secondary culture which is here, and it was 5% inoculum in this flask which was inoculated about 2 hours ago, and you can see there is a lower density of cells which is at the moment is 0.5. This is the typical optical density that we use for chemically competent cell preparation. And what we will do is that we will take about 30 ml from this culture into the falcon tubes, which are 50 ml falcon tubes, and as I mentioned earlier, we will take about 30 ml of this culture in one of the empty falcon tube that has been labeled for the preparation of calcium chloride competent cells. What you see here is the cuvettes. These quartz cuvettes will be used to determine the optical density of the secondary culture through spectrophotometer. Okay, and we also have a blank setting for that. This lauria broth, which is sterile at the moment, will be used for zero setting in the spectrophotometer, and we will compare this black versus the cells in this flask to see the optical density. This is the spectrophotometer that we will be using for determining the optical density of the cells. This equipment, when you turn it on, it is by default set at 400 nanometer. The optical density of the bacterial cells is usually measured at 600 nanometer, and you need to adjust that wavelength on this equipment before we take the optical density. So this is what she is adjusting now. Yes, it is set now to 600 nanometers, and she is now ready to put the blank, that is lauria broth, into this cuvette, into this place. Okay, and she will set this to a reading of 0. Okay, so it is now 0 set, and now we will replace this blank with the bacterial culture to look at their optical density. She has now the cells, bacterial cells, which were grown for the secondary culture, and she's going to put this quartz covered into the spectrophotometer. The same way she placed blank in there. And now which button you are going to press? So just reading. So we don't press any specific button for this calculation. We already set this OD 600 nanometer to 0 with Loria broth, and now you can see the optical density is 0.487, which is very close to 0.5, and we take the cells in the range of 0.45 to 0.5 for preparation of chemically competent cells. So the OD is perfectly fine, and we can proceed further for making the chemically competent cells. We just checked the optical density, and that was perfectly as desired. So now she's going to pour 30 ml of this culture into the falcon tube. This falcon tube is already graduated, so we don't need to measure these cells in a cylinder and put here. So she has just marked the 30 ml position on this falcon tube. Okay, so she will fill the liquid culture up to this point to make sure that this is 30 ml, and she will be balancing the centrifuge machine with a 30 ml of distilled water or just tap water, so that the balance tubes can be spun on the centrifuge machine. So we have taken, it's perfect, it's 30 ml, okay, and it is ready for spinning on the centrifuge machine. Okay, this is a Sigma centrifuge that can go up till about 10,000 RPM. The cells were collected in falcon tubes, and those cells are now ready to be spun for 4,000 to 5,000 RPM for settling the pellet. And if you see, the rotor in there is having two capacities, one for 50 ml tubes and the other probably for 15 ml falcon tubes as well. The RPM of this rotor have been set to 4,000 for a time of 5 minutes. Okay, so we'll put our tubes in there and we will start spin. The machine is attending the RPM. After it reaches 4,000 RPM, we will wait for 5 minutes, and then we will come back to collect the cells. So let's wait till the machine stops. Okay, the machine has been stopped, and we will take our tubes out of this machine. Can I see the pellet? Can you rotate the tube a bit? Yes, I can see the pellet. Actually, I need a contrast here. Yeah, it is quite visible. You can see it's a big pellet down there. And we need to decant now the supernatant from this, and we will suspend it in 0.1 molar calcium chloride, which is pre-chilled in ice. Okay, we are ready to decant the supernatant. You can drain it now. Can I see the pellet again? Yeah. Can you bring it a bit closer? Rotate it a little. Yeah, it can be seen actually. Okay, so you can proceed further for the addition of 30 ml of calcium chloride and You can start mixing immediately after addition of this solution into this tube, and we will see that how these bacterial cells are going to take a whitish tinge. E. coli usually gives a pale color upon pelleting. So, did it suspend well?
Yes, sir.
Yeah, the cells are now suspended in 30 ml of this calcium chloride solution. There is no pellet at the bottom. I hope it is very well suspended, and we can go for spinning of this tube for 5 minutes again at 4000 rpm, and we will see how the pellet appears this time. We are spinning it again for 5 minutes to get the cells pelleted after 0.1 molar calcium chloride treatment. The RPM will remain 4000, and the time will always be 5 minutes in these centrifugation steps. So let's wait till the machine stops, and then we will take out these tubes from here. The machine is about to stop, and we will see the difference in the pellet after calcium chloride treatment. If we get a fluffy pellet, it means that calcium chloride has treated the cell wall very well, and the pores in the cell wall might have increased. The pellet should be different actually from the one that we get from Gloria broth. So let's see. Open the machine and we will check it immediately. We can see that the pellet is whitish now, and it is spreaded out to the bottom of the tube, which is an indication that the cells have been treated well with calcium chloride, and they are quite fluffy as compared to a compact pellet that we obtained after first spinning. Okay, so now we will decant this 30 ml calcium chloride from here, and we will add 10 ml of calcium chloride to give a second treatment to these cells. Okay, so now you can add 10 ml of fresh calcium chloride to the pellet. And just resuspend the pellet again, and I will check the density of the cells just optically with eyes after the suspension of this pellet, and this gives an idea that how the cells after subsequent treatment with calcium chloride, they get whitish and more white with every treatment. Just very gentle resuspension is required here. Okay, so you can give a few swirls to the tube, and this will be completely resuspended. We can see that the turbidity of the cells is increasing. So we don't need to incubate them for a long time. Actually, the treatment has been given to fresh calcium chloride solution, and this tube is again now ready for a final spin at 4000 rpm, and we will suspend the final pellet in 2 ml for dispensing into append-of tubes and later usage for transformation into those cells. So you are ready to spin them now. the cells are now being spun for the last time before we get the final pellet and resuspend it into 2 ml of 0.1 molar chilled calcium chloride. So this spin is again at 4000 rpm for 5 minutes. Yeah. Okay, so we will wait till the machine stops and then we will come back here again. Okay, the machine is stopped and we can open. We'll see the pellet again. But after successive washings with 0.1 molar calcium chloride, what we are going to get. And here we can see that the pellet is now much more fluffier than before. Initially it was quite compact, but now we can see that cells are now shiny and whitish in color, which is an indication that calcium chloride is working well with these cells, and these cells are at the last final stage, and we will decant this calcium chloride from here and we will finally suspend it in 2 ml of calcium chloride for dispensing into a Pandolf tubes, and we can take 200 micro aliquots into the Pandolf then. She's decanting the liquid from the top. Can I see the pellet again? One more time. Can you take it out of the hood?
Contrast.
Need some contrast. Here we can see that the pellet is very well whitish and fluffy. Okay, so now you can add 2 ml of 0.1 molar calcium chloride to this one. We are trying to suspend this pellet in 2 ml of 0.1 molar calcium chloride, and the final step is then dispensing into a Pandolf tubes and keeping those tubes at minus 80 degrees centigrade till the cells are ready for use. So we will go to the other lab and we will dispense now these cells in the Pandolf tubes. That's perfectly fine. We are ready now to dispense those cells into the Pandolf tubes. Out of 2 ml, we can fill about 10 tubes with 200 microliter each. That is the standard volume of competent cells around the globe. That we use 200 microliter of competent cells per transformation reaction. So you can collect the tubes on ice. So you know what I usually do is that I write CC on the top. So that is the indication of competent cells. So at the end of this pouring, so I will appreciate if you can write CC on the top of the tubes so that we can identify that those are really the competent cells. So 200 microliter from this 2 ml is going to each of the 10 tubes. Close the top and label them accordingly. we can write in fact triple C here, chemically competent cells. And then we will have another version, electrocompetent cells, ECC. Okay, so that's fine. We can differentiate the two kind of cells. So these chemically competent cells are now ready. Okay, so we can see that they are 200 microliter per tube, and we will keep them at minus 80 degrees centigrade till they are ready to use in our next experiments. Okay, so this is the end of preparation of chemically competent cells, and now we will begin with electrocompetent cells, which is the second experiment. This is the beginning of experiment 2, and here is the culture of E.coli top 10 cells that we will be using for the preparation of electrocompetent cells. We don't need a secondary culture from here because we need a higher optical density of the cells always to keep the cell wall thick. So let's see what's the optical density of these cells, and we will measure the optical density the same way we measured for chemically competent cells. So let's see what is the OD of this culture of E. coli. She is pouring the Laurier broth into the cuvette that will act as a blank to set the spectrophotometer reading to 0. Okay, so we are ready to go to the spectrophotometer, and here it is. So it is already set to 600, and the reading is being set as blank by pushing 0 button here. Okay, so this is what she did. She pushed the 0 button so that a 0 reading can be obtained. That is 0.001. It is still okay, it's close to 0. So you can take out that tube cuvette, and now we will put those cells to measure the optical density of those. Here she is now pouring these cells into the empty cuvette, and we will determine the optical density of these cells the same way we measured for chemically competent cells at 600 nanometers. It's 0.943, 45, 47. So it's 0.9, which is the one which is required. The cells, they are grown to maturity. They are having thick cell wall, and these cells, if harvested and cleaned with water, they will very well tolerate the electric shock. So we can proceed now with the centrifugation of the 30 ml cells for getting these electrocompetent cells. Okay, we have got chilled water here, which is just out of the freezer. It was placed here about an hour back so that it should be sufficiently cold, and we have the cells. We will put these cells to a pre-chilled tube. You can take out the water in a Falcon tube and keep that tube in ice so that this water does not get warm over time. So you can take 30 ml of the cells the same way we took for chemically competent cells. Okay, perfect. Yes, she has marked it very well. So she knows that this is 30 ml position on the Falcon tube. So the measurement is quite good. And to balance this, you have a balance tube. Okay, we can take 30 ml water into this tube. place it in the centrifuge. This is all set, and we can go for a spin at 4000 RPM for 5 minutes. Let's go. We are back to the centrifuge, and we will continue the preparation of electrocompetent cells. We will spin these cells at 4000 RPM for 5 minutes, the same way we did with chemically competent cells. Yes, you can go ahead and put the spin for 4000 RPM for 5 minutes. So this will clear the cells from lauria broth, and then we will start washing with clean water, that is double distilled deionized water, especially for the preparation of electrocompetent cells. Okay, let's wait, and we will come back after 5 minutes. Okay, so machine has stopped, and you can proceed for opening the lid. So it will take a little while till it opens. Okay, so this is a very nasty sound actually. Can I see the pellet? Yes, it is quite visible here. Can you take it to the black background of monitor? We will see the pellet here at 4000 RPM for 5 minutes. We get actually an excellent pellet of the bacterial cells. We don't need to go for higher RPM. That gives a compression effect, and that compression can actually lyse the cells by disrupting the cell wall. Okay, so we are going to clean it for the first time with 30 ml of ice cold double distilled deionized water. She's going to decant this lauria broth from the top of this bacterial pellet, and she will be adding or resuspending this pellet now. You can see the pellet very clearly. Okay, yeah, it is very clear actually. You can see that. And she will pour now 30 ml of deionized distilled water. The purpose is to remove all the salts and all the ions which are there with the cells. We need very neat, clean cells for electroporation, so that the current that we apply for transformation should not harm the cells, but it should move the DNA from outside the cells towards the cytoplasm of the cells, where the ligation mixture having the closed circular DNA can stay within the cells, and we can screen them later on. Is the pellet suspended well? So when we make a pellet at low RPM, it easily suspends back. You can go ahead and spin it. We will do another spinning. We are ready to spin these cells after suspension in 30 ml water, and we maintain the same RPMs and time, that is 5 minutes for this spin as well. So the machine is attaining the speed, and we will be back to take out this tube in about 5 minutes when the machine stops. Okay, let's wait for that. Yes, the machine is stopping now. It will come to zero reading in a couple of seconds, and we are ready to take out the tubes, and that will be the pelleting of our cells, and we will start washing afterwards. So we'll give it 2 cleaning steps to remove most of the salts from there. Okay, so Okay, so you can open the lid, take out the tubes. Let me see the palette. So this is the first washing with 30 ml of clean water, right? And now we will clean it one more time with 30 ml, and then we will suspend it 2 ml finally, okay? So we are ready to go. She is going to decant the 30 ml of water, taking away most of the salts from bacteria. Okay, so give it a good drain, and now you can suspend it again in 30 ml of chilled water to remove any remaining salts from there. What she will do is she will resuspend the cells, the pelleted cells, into this water, so that the individual cells they get suspended very well, and all the salts which get associated with the cells will be removed very thoroughly. Okay, so it is a good suspension again very quickly. So that's the reason that we spin these cells at low RPM so that they can suspend very well, very easily. So we are ready for the second spin at 4000 RPM for 5 minutes. Place the tubes back in the centrifuge, and we will run it again at 4000 RPM for 5 minutes. The machine is attaining speed, and we will come back when the machine stops. The machine is going to stop in a few seconds time, and that was our final washing step. That is the second 30 ml washing step. Now the palette will be suspended in 2 ml of ice cold sterile double distilled water, okay? And that will be dispensed in 200 microliter liquids, and it will take about 10 tubes. So 2 ml of the competent cells, they can be dispensed in 10 pound of tubes. Okay, it is stopped. Just take all the tubes from there. Can I see the palette again? Against the black contrast of the monitor. Yeah, it is quite good, but it's not like that we prepared in case of chemically competent cell. That was quite spreaded out, and that was quite fluffy as well. But this one is quite compact. So there are differences in palettes between chemically competent cells and electroporation prepared cells. So there is a difference always. Now you can decant the 30 ml water from there, and I hope most of the salts they are gone out from these cells, and you can now pipette in 2 ml of water finally, so that we can dispense these cells into the pendulums and keep them at minus 80 degrees centigrade until we need these electrocompetent cells. So I hope you will label these tubes by ECC, Electrocompetent Cells. And we will take these cells to the next lab for dispensing into the pen of tubes, right? Okay. Yes, the cells have been suspended very easily, very quickly, without any effort. So that tells that there is no compression effect on these cells during the spinning process. I hope you are ready now to aliquot the cells into the Pandolf tubes. She's taking 10 tubes, 10 sterile tubes. They are autoclaved ones, right? So I will go to ice so that they can be cold when she pours in the cold electrocompetent cells in there. And she can label it afterwards after taking out 200 microliter aliquots into each of the tube from this 2 ml preparation. Set. Preparation of competent cells does not take too long, but you have to actually prepare the cells very well. You have to do the secondary culture and take the cells at right optical density. Okay, that is the prerequisite in the success of this experiment. Otherwise, we have seen those are just the spins that we are giving again and again, and some treatments. In the first case, for chemically competent cells, we use 0.1 molar calcium chloride, but in the case of electrocompetent cells, we just use very clean water, that is double distilled deionized sterile water, and that is all pre-chilled. We keep the cells to stop the metabolic processes within them as cool as possible. Obviously don't freeze those, but keeping the metabolic activity down helps to reduce the cells from releasing these ions into the water medium, which is where the cells have been suspended. And electroporation is really very, very effective in transformation. Most of the time we easily transform 25-30 kilobase size of circular DNA in those. So they are all labeled by ECC, electrical competent cells, and you can place them now at -80, and we will use those cells when we will be doing our transformation experiments. Okay, thank you. This is all about the second experiment for today.